Hyperloop is a new form of mass transportation that will set the standard for 21st century travel by connecting cities in minutes. It starts with a near-vacuum environment inside a tube, which enables high speeds and low power consumption by nearly eliminating aerodynamic drag. Inside that tube, battery-powered pods glide at speeds up to 670 miles per hour, comfortably, safely, and quietly, using our proprietary magnetic levitation and propulsion. After building and testing the world's first Hyperloop system, we are now focused on our commercial product. The key to our product is guided by a design that is elegant through its simplicity, future-proof due to its modularity, and guided by the principles of this century, not the last. To do this, we've moved levitation, power, and propulsion onto the pod. Our proprietary levitation engines make Hyperloop 10 times more efficient than the world's fastest maglev trains today. The engines contain arrays of electromagnets which lift and guide the pod within the track. Hyperloop also supports on-demand service and high throughput by having pods travel in convoys. Unlike train cars, pods are not physically connected, which allows for individual pods to have different destinations. Just like a car taking an off-ramp, pods can split off while the rest of the convoy continues on. The absence of moving parts on the track and the advantage of levitation and guidance on top of the pod allows for high-speed switching and convoying to take place seamlessly. These next-generation innovations not only enable ultra-fast speeds, but provide on-demand, direct-to-destination service, carrying tens of thousands of passengers per hour per direction at airplane speeds with zero direct emissions. Fast, effortless journeys that expand possibilities. This is Virgin Hyperloop.
Satellite internet technology makes high-speed internet available in remote or rural areas of the country. If you're looking into signing up for it, it helps to know how it works. There are 5 parts to the process. First is the device you're using, maybe a laptop or a smart TV or a gaming console. Second is your modem and router. These interpret the data signals into a form that can either be sent from or received by your device. Third is the dish, usually on your roof, which communicates directly with the fourth part of the process, the actual satellite, which is orbiting at 22,000 miles above the surface of the Earth. Each company has only 1 or 2 satellites serving the entire country. The satellite, in turn, communicates with the Network Operations Center back on the surface, so information is constantly traveling in a loop from your device to the Network Operations Center, and this whole process adds about a half a second of latency, or lag. That doesn't sound like much, but that's enough to make certain things difficult or even impossible, like fast-paced online gaming. Historically, satellite internet has come with slower download speeds than cable and fiber, and between that and the high latency, the industry hasn't had many fans. But things are looking up for satellite internet. Both major national providers have launched much improved satellites recently, and their download speeds are much higher than they used to be, up to 100 megabits per second in some cases. And it's about to get even better. Several companies have announced plans to fundamentally transform the way satellite internet works, using massive networks of hundreds or even thousands of low-orbiting satellites to deliver extremely high speeds with a fraction of the latency users currently experience, all within the next couple of years.
Medium Earth orbit, or geosynchronous Earth orbit. These 3 orbits are illustrated here. We will get into more details of them later. There is an interesting region in space called the Van Allen belt, a region full of highly energetic charged particles, which could seriously damage the electronics section of a satellite. Generally, it is preferred not to park satellites in the Van Allen belt. The decision on what orbit is to be chosen for placing the satellite depends on the application and purpose of the satellite. If the satellite is built for Earth observation, weather forecasting, geographic area surveying, satellite phone calls, etc., then orbits closer to the Earth are chosen. LEO is the closest to the Earth at an altitude of between 160 and 2,000 kilometers, and its orbital period is approximately 1.5 hours. But these types of satellite cover less area of the Earth, so many satellites are required to obtain global coverage. That's why, in the case of broadcasting, a high orbit such as GEO is chosen. Satellites in geosynchronous orbit are at a height of 35,786 kilometers and rotate at the same angular speed as the Earth. It means the satellite takes exactly 23 hours, 56 minutes, and 4 seconds to complete one rotation. Within the geosynchronous orbit, there is a special category of orbit called geostationary orbit, which is concentric to the equator of the Earth, sufficient to cover the entire Earth. Now, let's look at the main components of a communications satellite, along with their functions. At the heart of communication satellites are the transponders. The main task of a transponder is to clear in this animation. The graveyard orbit is a few hundred kilometers above the geostationary orbit. For this operation, the thrusters consume the same amount of fuel as a satellite needs for about 3 months of station keeping. The satellites we have discussed so far
Okay.